Okay, we're good to go. Okay, again, welcome. My name is Greg Thompson. I'm your counselor for the Astronomy Merit Badge. I'm an Eagle Scout. Like I told you before, Astronomy Merit Badge is the first one I earned when I was 14 years old. It might have been 13. I'm not absolutely sure. It was one of the first badges I earned. I got interested in astronomy. I took a lot of math and physics in high school and in college. I took one astronomy course in college. My career ended up being in computers, which is very related to astronomy these days. But I continued to pursue astronomy as a hobby and joined the Los Angeles Astronomical Society with my telescope, which I'm going to show you here in a little bit. And I do outreach and public star parties. Like I told you, at Griffith Park Observatory, at Mount Wilson and Garvey Ranch, we have observatories and star parties around the city. So I certainly invite you to check that out. The Los Angeles Astronomical Society out at Griffith Park Observatory is sponsoring this. The Zoom is paid for by them. And some of the folks that have joined, I think one member has already joined that's going to be sharing with you tonight. And I think Tim Thompson will be joining us, who's an astrophysicist, a little bit later tonight. So thanks to the Astronomical Society for hosting all of this and making it possible. So just stay on mute. If you have any questions tonight, please type them in the chat. Carolyn, who's sitting right over here on my left, will be monitoring the chat and will feed the questions over to me. If we're coming out of our observing session tonight and you want to go off mute and ask a question, that's okay. But while I'm whipping through the presentation to get you through the workbook, it's probably best if you just take the notes and fill out the workbook as you go along. So stay on mute, questions in chat. You can use the little hand icon to get my attention because I'll see that probably. And I think we're good. We've got a list of all the attendees. And so tonight's 3-hour class counts as requirement number 9 observing session. And for number 9, obviously you'll go in there and write in what we looked at tonight. It's going to count as your star party. It is virtual, and that's the live viewing we're going to do is pretty amazing because we're actually attaching a very high-powered astronomical digital camera to a telescope up in the mountains, and you're going to look through that live through a session tonight after it's dark. So we actually are doing a star party. We're just doing it over a Zoom. Last weekend, I went up to our dark viewing site. Dark skies is really important to astronomy. On the night of the Perseids meteor shower, so every August, there's a night when the Perseids, the Earth goes through the debris of this comet, and I think I saw about a dozen big crashing meteors through the sky. It's a really fun night, and I had a lot of fun sitting in my chair and waiting for these pieces of comet to streak through the sky. It's a really fun night. And we taught this class back in July and the comet was still visible. I don't know if you got a chance to see it. You're not going to get many chances to see a naked eye comet with a double tail. So when the chance arises, change your schedule, make it up to the mountains or the desert or go on a camp out or something, get your binoculars. It's truly a spectacular sight, and you don't get many chances in your life to see things like meteor showers and eclipses and comets. So if you're interested in astronomy, I'm going to give you some resources where you can know what's happening when, or when the star parties are, or when these things happen. Okay, so the next thing I'm going to talk about is how to earn the merit badge. Then I'm going to do a little introduction on how the sky moves around. And I'm going to go pretty quickly through this introductory material. When I start the PowerPoint, which is going to be the slide presentations I'm doing tonight, those are in order and they are numbered by the requirements in your merit badge book or in the requirements on your worksheet. So for the next 5 to 10 minutes, this is just general background information, not something you need to be writing down. But when I start the PowerPoint with number 1, you should have your workbook out or be taking notes, because by emailing me that workbook or sending it to me to my address, that's how I'm going to send you back a blue card. So the way it works is I sent you a copy of the merit badge workbook, and it's about 12 pages or 14 pages. We're going to be through just about everything tonight. So if you take some notes on the merit badge booklet itself, you're going to be good. There's a couple of prereqs where you have to make drawings. Of course, I'm going to expect you to make these drawings, and you're going to make these drawings, on your own time. There's a Big Dipper one that takes a couple hours, and then there's some moon drawings that takes 4 nights. So once you have your drawings in the workbook done and the rest of the requirements filled out, you can scan your workbook and email it to me. I'll fill you out a blue card, I'll sign it, I'll scan the blue card and send it back to you. And you can print out the blue card and that'll count. Of course, when I send you back the blue card, you still need to get your unit leader to sign it and fill in your address and stuff, but it'll all be signed and complete if your workbook is complete. If you would like the actual physical blue card, email me your address and I will actually mail you the physical part of the blue card that is yours. If you don't have a scanner to scan your workbook and drawings, you can take a picture with your phone. You can scan it through a scanner if you have one. If you don't have those resources available to you, just send me an email and I will email you my physical address, and you can drop your workbook in an envelope and send it to me, and I'll review it and I'll do your blue card the same way as discussed. So your main focus is going to be get that workbook finished. I want everyone in the class to earn the badge. So I'm going to provide additional resources for you, like the YouTube recording. I can give you copies of the slides, your merit badge booklet, but pretty much we'll cover every answer tonight that you need to finish that workbook. So I hope to hear from all of you by that's time. So the schedule tonight after this introduction, I'm going to spend about 5-10 minutes on sky maps and how the night sky moves around. You have to have a sense of when you're standing on the Earth looking up at the sky and the stars and the planets are slowly moving each day. Like, what is that motion? How does it work? What is it? And I'm going to talk about that next. So let's get started. So the stars in the sky, you go out and you look at the stars. Even in Los Angeles with the light pollution, you can see magnitude 0 and magnitude 1 stars. Hopefully tonight you'll see some stars. Anyone that gets a chance to spot Jupiter tonight during our observing session, or can get out and make out Vega up overhead, which is a very bright star. Even in light polluted skies, you can see these brightest objects, and I hope you'll be able to see some stuff when you go out in your backyard. We're going to be taking about a 15-minute break a little after sundown, and you can go use the restroom, get a drink of water, but you are going to go outside and see if you can spot anything. So these things move around from season to season and day to day. If you stood in one spot and just looked up at the sky and waited a few hours, you would notice the sky wheeling around, all the stars together spin overhead like a dome above the Earth, or a giant record spinning around. So it all spins around one particular spot in the sky, and that motion completes one circle in 24 hours. And that's a clue to what's really going on. It isn't really the stars wheeling around in the sky. It isn't the sky that's moving. You're standing on a giant ball that's spinning around, and it's spinning every 24 hours, but you feel like the Earth is not moving. You're just standing there, and it's the sky that's wheeling. But what's really happening is the Earth is spinning around, and you're looking up, and if you stood there for 24 hours, everything would end up back where it started. This is why the sun rises in the east and sets in the west. Everything rises in the east and sets in the west, because that's the direction that the Earth spins, is towards the east. So everything spins around a particular spot in the sky. You think of the Earth as a large globe, and you put a line through it, a pole, and you went up to the North Pole, it would stick out of the Earth and point up at the sky. And if you extended that pole all the way into the heavens, that would show you the point around which everything slowly wheels around. And that line, or that pole, points at a particular star in the sky, the pole star. And it's the one star that doesn't move, because everything else spins around it. It's at the center of the motion, or relative motion. So finding that star tells you a lot. The things that go around that star go around it. You can see it. The famous constellation, the Big Dipper, where the two stars point at the pole star, wheels around the pole star every night slowly, and everything moves around. And in addition to that, night after night, the stars all keep their same positions, right? The Big Dipper is always the Big Dipper. It doesn't change shape from night to night. The stars don't move in their constellations. That's why we call them the fixed stars. Now, of course, if we lived for 1 million years and you could travel in a spaceship to 1,000,000 years in the future, the stars would look a little bit different. Actually, there is a little bit of motion because the stars are all in the Milky Way. And I think all the stars in the Milky Way take about 200 to 300 million years to make one complete circuit around our Milky Way galaxy. So the stars for our lifetime are never going to move. So we call them the fixed stars. But if we lived a really long time, you could probably see the stars moving around a little bit. But the planets, the moon and the planets, they change their position because they're moving relative to us and the stars. So night after night, if you go out and look, Mars will be in a slightly different position. Jupiter changes position slowly because it's very far away. So it moves like not even the width of your pinky finger from night to night. Mars moves a couple of fingers from night to night very slowly. Venus and Mercury move a little bit more quickly. And the motions of the planets, when ancient astronomers looked up, the planets seem to wander around the constellations. And you know, if you waited many years, Jupiter would, you know, change its position throughout all these constellations. So they called them wanderers. And that is what the word planet means in Greek. It means wanderer. So the planets not only wheel around every 24 hours, night after night, day after day, week after week, month after month, the planets actually move their position. So if someone says, oh, Jupiter's in Sagittarius this month, which in fact it is, and you'll see it tonight, what that means is that right now, the Earth is in a certain position on the sun. Jupiter is out past us on the same side of the sun, and relative to us, Jupiter appears to be in the constellation Sagittarius. But as we move, and Jupiter moves, that position is going to change. So I've got a couple of sky map here things to show you here. I'm going to show you one of my favorites here. I give these away to scouts, so if I see you at Garvey Ranch, you get one for free. This is a little sky chart, and I like this one because you can rotate it to what time of night, and you can see the Milky Way spinning around. You can see things rising and setting. So you can use a sky chart like this, set it to the exact time, hold it up to the sky, and it'll show you exactly what's visible in the night sky. Some people call these planispheres or sky charts, night sky charts. They're really, really handy, especially if you're going out camping or something to see what you can see. You can see there as I'm wheeling it, there's the Milky Way, which is our galaxy, wheeling around the sky. Now, you can guess this little pin right here. See everything spinning around that pin? You guys probably have guessed what star is where that pin is. That's Polaris, or the North Star, the pole star. And this motion is the Earth spinning around underneath the North Star. So that's one type of chart. The chart I sent you an email, which I will share with you now. I'm going to talk about that a little bit. See if I can get my sharing going here. Okay, this is the one I mailed you. This is the evening sky map for August 2020. You can go download these from the Night Sky Network for free on any given month. So if you're going on a camp out next year and you think you might want to do some stargazing, go grab this month's star map because it'll show you where the constellations are and at a particular time. So the sky map is usually geared for about 8 p.m. to 9 p.m. in the evening, like after the sun goes down. But we're going to look at this map real quick. If you can see it on the screen, great, but you should have your own copy if you have a chance to print that out, because there are some constellations and stars here that we're going to be filling out in the workbook a little bit later. So the first thing to do is to locate the North Star. So in the upper right, you should see Ursa Major, which is the bear with its legs and its skinny neck. I don't know, it doesn't look like a bear, but it's an upside down bear. Within the bear is the Big Dipper. It's labeled there, the Big Dipper. And the Big Dipper is the handle and the little cup. And you see that the outer two stars of the cup, they've drawn an arrow over towards the North Star in Ursa Minor. Well, this is a good way to find the pole star. If you can find the pole star in this night sky, you don't need a compass because the direction of the North Star is north, of course, because it points towards the North Pole. So as you walk on the Earth towards the North Pole, it rises higher or lower in the sky. So by measuring the angle from the horizon to the pole star, you can determine what latitude you're on. If it's very high in the sky, you're in a high latitude, which means you're up in Canada or Alaska or something. If you have a very low angle and the North Star is close to the horizon, it means you're closer to the equator. So in 5 seconds, you just learned how to navigate the Earth. And you can also tell time too if you know the constellations well. So this constellation, the Big Dipper and the North Star, they are visible in Los Angeles. You do need a clear, dark patch of sky off to the north. When we have our break tonight, extra points if you can find the Big Dipper and the North Star. That's a really good one. Off to the south, if you have a clear view to the south, this is going to be towards the bottom of our sky map. First, I want you to see that blue band across the map. That is the Milky Way galaxy, which is 100,000 light years across and only 1,000 light years in thickness. So the Milky Way is like a giant flat pancake. And the reason it appears in the sky as this band across the sky is that we're in the Milky Way looking out along the edges of the pancake. So we see all these stars in a band, and that band goes all the way around the Earth. And the center of the Milky Way galaxy is in Sagittarius, which you'll see the teapot is that constellation down towards the bottom of the star chart. If you can spot the constellation Sagittarius, you know you're looking in the direction of the supermassive black hole at the center of the Milky Way galaxy. You'll also notice there's a dotted line, which is the ecliptic, which is the line of our solar system, right? The solar system is also a disk. So all the planets and the sun and the moon, they all follow along that dotted line. You'll see Jupiter and Saturn right next to Sagittarius. So if you can get oriented to the south tonight and spot Sagittarius and Jupiter and the center of the Milky Way galaxy, that would be super extra points, depending on how dark your backyard is. Off to the right of Sagittarius, the teapot, is a really good view right now is Scorpius, which is the scorpion. This is a constellation that's only visible in high summer. It'll be gone by this fall because the Earth will keep moving around the sun. But you see the 3 stars are his head, and then his long body tails around to his pointed poisonous tail. And if you can see the whole tail right now, it's visible, but you need a clear view of the southern sky. The star I want you to look for is the first big star in his body behind the T of his head, and it's labeled on this in tiny little letters, Antares. Antares is a super giant red star that's not that far from the sun. It's actually pretty far, but it's a very bright star, and it's clearly red. And maybe it'll look pale orange to you, but it's very different than most of the other stars. We call that the beating heart of Scorpius, the red star Antares. And that's another star that we'll be putting on our list. So you can wheel on around and look at other constellations. Over on the left, you'll see the great square of Pegasus, which is a pretty big constellation. And out in the tail of Pegasus is the Andromeda Galaxy. And it's labeled there with a little circle, M31. That's the biggest, nearest galaxy to our own. So when you look at the Andromeda Galaxy, every star you see in the sky is in our galaxy. It's our neighborhood. But looking at Andromeda is a completely different animal. You're looking at another galaxy. And Andromeda, instead of being a few tens of thousands of light years away, like most of the stars in the Milky Way galaxy, it's 2 million light years away. Now, that sounds like a really far and long distance. It's a tremendous distance. You almost can't imagine it in your head. But compared to the intergalactic distances of the Big Bang, Andromeda is essentially our next door neighbor. There are millions and millions and millions of galaxies that are much smaller and fainter and farther away. And those were all discovered up at Mount Wilson and studied by Hubble, and who figured out they were all flying away from us. And by thinking backwards in time, that's where they came up with the Big Bang Theory. So that is my tour of the night sky. I also want to share with you one other thing real quick. I know a lot of you guys have, yes? Oh yeah, I got to unshare to show you that. Oh, come on. Oh, it won't go back. Oh, that was stop share. There we go. All right. I'm just going to hold my cell phone up really quick. This is Sky Safari. There's a bunch of these apps that you can put on your smartphone and will help you find things. Sky Safari has a free version. There are several other free ones. I like Sky Safari, and they have a pro version that costs a little bit of money and has more objects. And it actually, the database keeps updating when comets come around and the planets that move and stuff. So you can use your cell phone, point it up at the sky and move it around, and it'll show you exactly what you're looking at. So if you see a bright star or a fuzzy patch or a comet or something, you can use those apps to identify them and help you find things. So those are pretty convenient. They didn't have those when I was a kid. We had to use our star maps and wheels. So that's my quick tour of our Earth and our solar system and our Milky Way and how to find things in the night sky. The next thing I'm going to do is start up our PowerPoint. And so we're going to be starting on earning the badge now. All right. So you guys should be seeing the PowerPoint presentation now. And this is just this is our online Zoom class hosted by the Los Angeles Astronomical Society. I'm your counselor, Greg Thompson. To complete the badge, read the merit badge book, complete all the requirements in the workbook, and then complete a signed blue card, and we'll do that virtually. Don't get a partial, because if you send me an incomplete worksheet, I'm not going to send you a blue card back. I'll send you a note saying, hey, you missed number 8. So send me a complete workbook and you'll get the badge, and that'll be cool. I do want to point out, in the upper right of this slide is a picture inside our Garvey Ranch Observatory in Monterey Park. So if you ever get a chance to come to one of our open nights on Wednesdays when we're out of this COVID thing, this is the telescope that you'll be able to get a look through, and some other stuff. We also have a machine shop there where we make and repair telescopes and grind lenses and do all kinds of cool optical stuff. There's like 100 telescopes laying in pieces all over the place. And we have a classroom there, and it's over in Garvey Ranch Park, so it's not very far away. All right. So I'm now starting with number 1. And I'm not going to spend a whole lot of time on the hazards, because you guys are scouts. You got a scout handbook. So you know how to do things like heat exhaustion and all that. You can look some of this up in your scout handbook, as well as the merit badge book. But starting with 1A, explain to your counselor likely hazards. Well, I've got these kind of listed out. My number 1 injury for astronomy is not exactly skydiving when it comes to danger, so I'm not going to dwell on this too much, but it does happen at night, in the dark, outdoors. So this is your most common hazard, is stumbling around in the dark. Is you hit your head, or you trip over a telescope, or you bang up your knee, or it's real, So I'll call that, my first answer to this is stumbling around in the dark. But you do need proper clothing, because it can be really cold. Astronomers in the old days have frozen to death in the domes of their telescopes. It has happened because the best viewing is high in the mountains, and cold winter nights are a great time for viewing the sky. So you do have to wear proper clothing and all that. How to prevent and how to treat stumbling around injuries. So my answer to this is to use a red light. We don't use flashlights at star parties around telescopes, because bright white lights like flashlights and headlamps will ruin your night vision. If you don't know this, after about a half an hour in the dark, your eyes open up and you can see better in the dark. If you shine a light in someone's eyes, that goes away almost instantly. So astronomers use red lights, and you can prevent stumbling around in the dark. Get a headlamp or a flashlight that has a red light setting, and then that's how you go to star parties and work around telescopes. So you can prevent those. If it does happen, how to treat them: standard first aid for twisted ankles and skinned knees, which is going to be treating the wound and making sure it doesn't get infected and putting a Band-Aid on it and that sort of thing. Another one you could list if you want to, it's not on the slide, is altitude. If you're up in the mountains, even up at Mount Wilson, you're up at over 5,000, 6,000 feet. that's high enough for the altitude to affect people, and they can become quite ill. And altitude sickness, generally paleness, sweatiness, shortness of breath, dizziness, and nausea. If someone goes from a low altitude to a high altitude and does physical activity and exhibits these symptoms, it could well be altitude. So you need to rest, and if it's serious, get to a lower altitude. One of the hazards of using a telescope is if you were to point binoculars or a telescope at the sun, you would be magnifying the sun by hundreds of times. That light would go straight back to the retina in your eye and damage your retina. So this is actually a significant hazard. So protect your eyes. Don't look at the sun. Especially don't ever point a telescope or binoculars anywhere near the sun. And to prevent this, you can use projection pinhole cameras, camera obscuras that display the sun if you want to look at an eclipse through a little box or piece of cardboard, and it'll display a picture that you can look at indirectly. Obviously, if you have correctly rated solar filters for your telescope or the little glasses, if they have the right gel material and they're approved, it is then safe to look at the sun. But please be sure, don't think you can put on a pair of sunglasses from the pharmacy and stare at the sun. Those are not going to protect your eyes. You have to have actual eclipse glasses with the correctly rated filter. One other thing I'll mention, because you have to go to star parties these days, you will see people use the lasers to point at things in the sky. It's super convenient and easy and to help people see things, to use a laser to point things in the sky. I just want to point out to you guys that those are illegal, that the FAA has banned them because they can bounce off of planes and shine in the eyes of pilots. But another reason is those lasers are actually powerful enough to damage your retina. And, as fun as it is to play with lasers and pretend like that they're, Star Wars or whatever, if those lasers get pointed anywhere near someone's eyes, they could permanently do some damage to the vision. So I generally prefer not to have lasers around star parties with scouts, because as fun and cool as it looks like, they're not entirely safe. But if you do have someone using a laser at a star party, you just want to be sure that they only point it at the sky and that they never turn it on when it's pointed anywhere near people. So those are my answers. There's a couple more in your merit badge book. So summing up, number one, darkness, stumbling around, cold and exposure, altitude, and looking at the sun, and the use of lasers. That's like 5 hazards of astronomy. What should you do? I covered those. Use a red light, be aware of your surroundings, dress warmly, be prepared, have water, move to a lower altitude, and that sort of thing. So going on to 1B, and I'll start light pollution just a second. I want to make sure you guys got the one covered. Going on to 1B, a lot of this stuff you could look up in your scout handbook. Pretty straightforward stuff. Heat reactions, if you get heat prostration or heat stroke, not very likely in astronomy since it's mostly a nighttime activity, but get people in shade and get them some water and follow the standard treatments. Cold reactions, warm them up, get them indoors, maybe a hot drink. If they actually have a lack of blood circulation in their fingers or toes, you need to get them to help, because that could be frostbite and a little bit tricky. Dehydration has happened. I've seen it many times at summer camp. I guess if people go out and they get excited and stay up all night and don't drink water. But dizziness and nausea are very common, and you just got to drink water, sip water, and they'll recover if it's not serious. Bites and stings, identify what's bitten you. If you've just been bitten by a bee, use a credit card or a piece of cardboard to gently scrape the stinger out. If you've been bitten by something more serious, be sure and identify it and seek medical help if it's serious. Damage to your eyes, cover up the eyes and seek medical attention if someone goes blind or looks at the sun too much. C, describe the proper clothing. Since astronomy happens at night and it's typically cool or even cold or high altitude, we want to dress in layers. Be sure you have a hat and gloves and a red light so that you can see when you're walking around in the dark. Observe how to safely observe the sun. We already covered that. You are not going to point your binoculars or telescopes anywhere near the sun. If you do, you're going to use either an indirect projection method like a pinhole camera, or you're going to use a gel filter or an approved solar filter that blocks out a significant percentage of the sun, like the eclipse glasses that we use. So that gets us all through number one. You fill those answers out and you're good. Going on to number two, what is light pollution? So people don't really think about light pollution because, you know, it doesn't cause asthma. But this is a picture of Los Angeles that I took from Mount Wilson, I think it is. And look at all these lights. So we're burning train loads of coal and to light up our city, to point all these lights up into the sky. So even if it isn't directly adverse to our health, it's a giant waste. Like all the smoke and all the smog and all that stuff to generate all this light is unnecessary. And if we were to update our lighting system and not point all these lights up in the sky, we would be saving money and cleaning up our air, and we wouldn't have all this light which shines up into the sky. So what happens when this light pollution or this light shines up in the skies from human activity in cities mostly is it creates a background of light in the sky that washes out, is brighter actually than most of the stars, the Milky Way, and the faint objects. So most kids growing up in cities never see the stars. You know, when I do star parties at schools in the Los Angeles Unified School District, a lot of those kids have never even seen the Milky Way. They've never seen the beauty of the night sky out in the desert or high in the mountains. So they don't really know what's up there. And, you know, so when they look through a telescope, it's the first time they've ever seen a planet or a nebula or a galaxy. So light pollution is kind of serious. What happens also is we have a lot of smog and regular air pollution. The light that comes from our street lights and our buildings and our car lots and our 7-Elevens shines up into the night sky needlessly. And then it hits all the little particles of smoke and dust and pollution and shines back down on the earth as a reflection. And that creates even more sky glow, again, washing out everything. So how can air pollution affect astronomy? It essentially ruins it. You can't do astronomy if there's a lot of air pollution and light pollution. Because the light pollution and the air pollution block out our vision of the night sky, and we can't see things. And it affects telescopes as much as it affects people. So, you know, it's a real problem, and we probably need to redesign our lighting systems to not waste all that light and shine up in the sky. And I'm a big fan of dark skies. I love seeing the night sky, so I would prefer if we didn't have all these bright lights in the city. So I often go up to the mountains in the desert or campouts to look at the night sky. Okay, so that's your answer to number two. It's pretty easy. It's covered in your merit badge book. Number two, that's that one. Okay, so now we're going to enter the section of number three. So in your workbook, you're going to see there's a picture there of a telescope and some binoculars. I'll talk about the binoculars first, and I'm skipping down a little bit here. Let's talk about the types of telescopes first, okay? And then I'll tell you what kind of telescope a binocular is. Okay, so the kind of telescope that's displayed in your workbook and in the upper right, the picture, that is a refracting telescope or refractor. And you can see that the incoming light hits a primary lens. And that means that refracting telescopes and binoculars have a curved piece of glass in front where the light enters the instrument. That curved piece of glass slightly bends the light at an angle, concentrating it down at the eyepiece. So that process of bending light is called refraction. And it's the same thing when you put a stick into water and the stick looks bent. The reason it looks bent is the light coming into your eye from that stick is slightly bent by the surface of the water in the same way it's bent when it hits the curved glass of the primary lens. So if you look in a telescope and you look in the front of it, or you look in the front of a pair of binoculars, and you see a big piece of glass there, you know it's a refracting telescope, because the next type of telescope doesn't have that at all. It doesn't have a curved glass in the front. So refracting telescopes are typically long and narrow. They usually don't have a very big diameter, because it's really, really hard to make precisely ground lenses bigger than, 5, 6, 7, 8 inches. Back in the day, they made some really big ones that were 20 inches. And yeah, I think the biggest one I ever heard of is 30 inches across. But that one was so heavy that as it moved around, it actually changed shape. So they couldn't make them any bigger. But they're very long and narrow. The picture I showed you from Garvey Ranch Observatory, that long, narrow telescope, that is a refracting telescope. I think it's an 8-inch. And when I say it's an 8-inch, what I mean is the lens is 8 inches across. The tube has a diameter or light gathering ability of 8 inches, right? So the primary lens bends the light into a cone, concentrating the light to the back of the telescope. So in refracting telescopes, typically you look through the back of the telescope where the light has been concentrated. The light is shined into an eyepiece to allow it to focus, and then you can look at objects in the sky, and they appear much closer and much brighter. So you can see things you can't even see with your regular eye, because it gathers and concentrates more light. It's like having an 8-inch telescope is like having a eyeball 8 inches across. It's just way better at gathering light. You can see way more detail, fine detail. So a refracting telescope and binoculars are like two refracting telescopes stuck next to each other. So you have a refracting telescope on each eyeball. And what it does is it allows you to use both eyes. Whereas with a regular refracting telescope, you can only use one eye. Binoculars are a great instrument for looking things at the sky. I really had good luck looking at the comet last month using my binoculars. So that really worked out. So the second kind of telescope, and let's see, 3A, explain why binoculars and telescopes are important astronomical tools. Well, by gathering more light and concentrating that light, they allow you to see things and details that you could never see with your naked eye. So they're really important astronomical instruments because they make your eyes more powerful when you look through them. Demonstrator explain how these tools are used. We'll be doing that demonstration in a minute. But basically, you look through the eyepiece or attach an instrument to the eyepiece. Going on to 3B, describe the similarities and differences of several types of astronomical telescopes. So the first one you learned is refractor. Refractors have very fine focus, and they are good at giving you sharp contrast, and they're not so good on fuzzy distant objects where you need a lot more diameter. So they're great for stars and planets, and you can get really good views of star clusters and some nebulas with a refractor. But for really faint objects, you're going to need a much different type of telescope. So the second type of astronomical instrument or telescope I'm going to talk about is a reflector. So the two words are very similar, but reflectors are completely different than refractors. A reflector does not use curved glass or a lens at all. The front of a reflecting telescope is just an empty tube. At the bottom of the reflector is a mirror. And so that's why we call it a reflector. A curved mirror at the bottom of the telescope bounces the light back up the tube of the telescope into another cone, and then a small mirror, angle mirror, kicks the light out to the side. So typically a reflecting telescope you would look at, and I'll show you a picture of one in just a second. A reflecting telescope, you would not look through the back of a reflecting telescope. You would look off to the side near the front where the eyepiece is. So the summary is refractors use lenses, reflectors use mirrors. And because reflectors use mirrors, they're way bigger. They can be much larger. So for example, my personal reflecting telescope has a 10-inch mirror, and it's not even that big by the standards that you can do. I think up at Mount Wilson, one of the most famous telescopes in the world, that is a 100-inch. Palomar, 200-inch. So these are mirrors that are, you know, bigger than you are. They're humongous. And it gives them the ability to gather very, very faint objects. So all the big research telescopes that look at distant galaxies are reflectors because of their ability to gather weak light. So reflectors are good for looking at like distant nebula and tiny galaxies, the things that are so hard to see that you need a huge mirror to gather the light. The third type of telescope is catadioptric, or also called a Cassegrain, which is a hybrid. It has a mirror in the back, but it also has a lens in the front. So these are fat, stubby telescopes that you'll see, and they kind of have the advantages of both and the drawbacks of both, but they are not as big. So you can get a pretty powerful telescope in a small profile if you get like a Celestron C8 Cassegrain telescope. They're pretty cool, and they're available commercially for hobbyists. Typically not used too much. Some people use them for advanced astrophotography, but the really big professional scopes are mostly the big reflectors. Okay. So describe the similarities and differences of several types of telescopes: refractors, reflectors, and Schmidt-Cassegrains. C, explain the purpose of at least 3 instruments with astronomical telescopes. So I've listed some instruments for you here. Obviously, the mount is really going to matter. Remember we talked about the sky moves at night? Well, if you don't have a mount that you can move the telescope with easily, you're only going to be able to look at your star for like 30 seconds, and then it's going to move. So a lot of mounts have gears and motors on them, so they move in unison with the sky. A polar equatorial mount is a typical type of mount. So that picture of the refractor on the slide, you see those counterweights and how the telescope can spin around that axis. If you point that axis in the North Star, it's really easy to rotate this telescope around as the objects in the sky move. So that mount can actually track the sky, which is really critical for taking a picture or exposure, or if you want to stay on an object for more than a few seconds. An Alt-Az or Dobsonian mount, which is my telescope, it just goes up and down and left and right, and you just point it. So it's not the same as a polar. Instruments that you can mount on a telescope is a finder scope, which is a small telescope or a viewer that allows you to spot your telescope in like you would use a scope on a rifle. When you look at the sky through a powerful telescope, you're looking at a patch of sky, depending on the power of your telescope, about the amount of sky as looking through a coffee stirrer held at arm's length. It's really hard to find things with that, right? You're looking at such a tiny piece of sky, it's hard to point it. So if you have a small finder scope on the side of your telescope, you put the object you want to look at in the crosshairs, and then you can see it through the big one. So almost all telescopes use finder scopes. Obviously, we put cameras. Back in the day, they were film cameras. Today, they're digital cameras. And they take all kinds of really cool pictures that you can stack, and you can see all kinds of neat stuff. I've seen some amazing digital photography in the club. It's called astrophotography. That's the hobbyist end. At the high end, this is what astronomers and astrophysicists do to study objects in the sky. A spectrometer is a really important instrument that you can put on your telescope, which divides the light into its color spectrum. Why is that important? And this is exactly like a prism. You know, you shine a light through a prism and it breaks it into red, green, blue, right? This is what a spectrometer does. But there's something really special about spectrometers. The amount of light in the different color wavelengths can tell you what the source was made of. What that means is if you fuse hydrogen and it shines brightly as a plasma like in a star, hydrogen only shines in a few wavelengths. It spikes up in certain wavelengths. So you take a spectrum of a star and you can actually tell what elements it's made out of. Even if that star is 100,000 light years away or more, and the light you're seeing is from the time of the dinosaurs or something, you can still split that light into the spectrum and say, hey, this star has this much hydrogen and this much helium and this much metals and all that kind of stuff. So spectroscopy, I said that wrong, spectroscopy is a really important instrument for studying the night sky. However, keep in mind that light is not the only type of electromagnetic radiation, or EMR. Light is just one set of bands in a much wider band of wavelengths, right? Well, you can't see microwaves or radio waves or X-rays, but they're the same kind of waves. They're electromagnetic waves. They move at the speed of light. They're just like light. They just have a different wavelength. You know, they vibrate at a different frequency. And these other wavelengths, objects in the sky, do glow in the microwave, in the radio wave, and the X-ray spectrums. But we obviously can't see those spectrums with our eyes, so we need special instruments. So over on the right of the slide you're looking at, you'll see this giant dish with a big focus in the front. That is a big metallic disc designed to concentrate radio waves. No, they're not listening to the latest Pop 40 station. They're actually listening to things like neutron stars spinning around and putting out radio waves, or supernovas going off that put out a whole bunch of X-rays or whatever. So it's important that understand that you can attach different kinds of instruments to your telescope, and from that, learn things about what's out there in the universe. We just covered like 7 different kinds of instruments. Feel free. It says you only have to list 3 of them. So whichever 3 you like, just put them in your workbook, but try to say something about what they're for. So 3D, describe the proper care and storage of telescopes and binoculars, both at home and in the field. So this is a super easy one. Storage means, you can see I have a little slide there of someone whose lens case. These are delicate optical instruments. They're easy to scratch. If you get dust on them, it messes them up. So you always put your binoculars with their eye cups back in their case when you're done at night. You put your telescope away to protect your mirror or your lens. You put your eyepieces in their carrying cases to prevent them from getting scratched. The same way you would take care of a pair of glasses or whatever. So it's just basic, keep them clean, store them away, put the covers on, and put them in their case. And the world's best scientists do this, as well as those of us that go out to look at the night sky. So that takes us up through 3. And I got a couple more slides that are just going to go over the instruments again while you're filling out your workbook. So I've got a slide here on reflecting telescopes to give you like a real sense of what a big reflecting telescope is. So on the left, that giant engine looking thing is a telescope. It's a really famous telescope. It's one of the first big reflecting telescopes that was ever made. It is up at Mount Wilson above Pasadena. You can see Mount Wilson at night up there on the mountains, the domes. That's the dome you can even see from Pasadena. So that is a 60-inch mirror. This telescope was installed about 100 years ago, if you can imagine. It spins around, and there's a mirror in the bottom there. You can actually see that just above the black at the bottom is this giant mirror. And the light comes in through the dome, shines through that lattice work, bounces off the mirror in the bottom, reflects back to the top in a ever-decreasing cone. And if you look at the top, you'll see a little black secondary mirror. The light enters that secondary mirror and is bounced out of the cage where the astronomer would sit way up in the air up there. This telescope is so heavy that in order to move it, they had that giant gray thing at the bottom that has the gear and the setting for this thing to rotate around and track the night sky. Regular gears would have had too much weight on them, so they had to float it in a bath of mercury, like an ice cube floating in water, to reduce the friction. And they actually just takes, you can turn that whole telescope with one tiny little crank the size of your hand. Obviously, it moves in 2 directions inside the dome. That is the 60-inch telescope at Mount Wilson, and it was about 25 years later they installed the 100-inch. In the upper right of this slide, you can see what I'm talking about. The light comes in that diagram from the right, goes down to the primary mirror. In this case, it's a reflecting telescope, bounces back up in the ever-decreasing cone, hits the secondary, which is an angled mirror that pushes that cone that light out the side and into the eyepiece that you can look at or attach an instrument to. The other big slide there, you probably recognize that's the Hubble Space Telescope. You guys now know how the Hubble Space Telescope works. It is a reflecting telescope the size of a school bus in orbit around the Earth above all the light pollution and atmosphere, so it takes really great pictures. One of the most amazing scientific instruments ever built by mankind. And they obviously have digital cameras to gather the images as digital data. Okay. This is Constellation and Stars. Do we want to stop and do our demo, Carolyn? Yeah. Okay. So I'm going to stop share. So we're stopping at number 3. You can take a rest from your workbook. I'm going to do a demo of some of my gear at this point. Just show it to you so you can see what mine looks like and a few things that I use. And when we're done with this demo, we'll resume the slides with number 4, which is going to be your constellations and stars. Okay, so I'm going to get up and go over by this telescope. Yeah.
All right. Camera on you.
Let's go over to this side. Okay. Let's bring that down a little bit, Carolyn. Oh, that's good. Perfect. Okay, so this is my 10-inch reflecting telescope. As you can see, there is no primary lens in the front, and down at the bottom, I don't think I can get it low enough for you to see.
Where's me stop?
Oh, there you can see it. You guys see the mirror in the bottom? Right? So you can see I'm able to spin it up and down, that's altitude, and left to right, that's azimuth. This is not a tracking telescope. It doesn't have a motor or a computer. And to look at things, I just have to point it at the night sky and keep moving it as things move. But it's really easy to use. You can learn how to point this telescope in like 1 minute. So what's on this telescope? Well, the light enters from the sky, right?
Okay.
It enters from the sky, bounces off the mirror, back up here, and you can see right here is the secondary, which puts the light out here, and I'm going to go up like this, and here is the eyepiece right here. So this is where the light comes out the side of the telescope. Here's my eyepiece, which is actually, this is a big 2-inch eyepiece, so it's really easy to use. And here is the focus knob, in and out, to focus the light into a nice crisp image. But there are a couple other instruments that I use to find things on my telescope. I have 2 finder scopes. I have a Telrad open view, which is basically just a heads-up display with some red circles. And this allows me to get, this allows me to find a particular patch of sky really easily, or like I can just drop Jupiter in there, real problem, no problem. For fainter objects, I use this finder scope. It's a 50 millimeter. It's actually a little telescope in its own right. Can you see that sticking out? Right there. So that helps me find fainter objects. So what I would do is start in the Telrad to get to the right place in the night sky, go to the 50 millimeter to center up, and then find the object in the eyepiece. This telescope gets really great views of planets and some of the fainter galaxies and nebula, especially when you get out of the city and away from the light pollution. So I want to share with you here's a mirror that you can see. So this is a curved mirror. Like, how do curved mirrors concentrate things? You see that? This curved mirror is concentrating light. So that's the kind of mirror in the bottom of a reflecting telescope. Here are my binoculars. Binoculars are a great instrument. Mine are a little bit large, which is that they gather a little bit more light so you can see fainter objects and magnify them a bit more. These are 9x63s, so they do a little more magnification, a little more light gathering, but they're also heavy. And it's really hard to hold your hand steady. So if you have something to prop your elbows on, or you have a tripod, binoculars work even better. When I went up for the Perseids, we put a pair of binoculars like this on a tripod. We were able to see the moons of Jupiter, which was a lot of fun, just through regular things. With regular binoculars, you can see the Andromeda Galaxy, you can see craters on the moon, and they're much more lightweight than dragging a telescope around. So binoculars are a great way to get started. Just take care of them and get a good pair. You can use them for all kinds of stuff in scouting. Okay, let's see, what else do I have to show you? I want to show you my digital camera. I do have a way to take pictures with my telescope. I'm just getting good at this. There's people in the club that are way better than me. Can you see this little thing? Yeah. So this attaches right here and has a USB cable that goes into my laptop. This takes a 20 megapixel picture, and it can take like 1 a second. So I can take dozens of these high resolution digital photographs, and then I can use software to combine them into amazing images of the night sky. So I'm still learning this and I'm getting better at it, but you can see this up in action out at Garvey Ranch. They make lower resolution ones that are quite inexpensive, but remember, you're gonna have to have a good tracking mount for these to work. Otherwise, the night sky is moving and the cameras don't work. So you gotta have a good mount to use one of these. Here's my red light headlamp, right? So hands-free, but not white light, right? Here's my compass, which I use to align the mount of my telescope with the north so I can get good tracking. Always good. If I can see the North Star, I don't really need this though. Okay, so I have a few other objects on the table here I want to show you. Can you get down on this, Carolyn? So this is a high quality star map. It's like an atlas of the stars to find the fainter things. So I happen to have right here, this is a map. Here's the Milky Way, this blue, and just off the edge is the constellation Orion. And this map shows hundreds and hundreds of stars that you can't see with your naked eye. And you can see these nebulas, and here's the belt of Orion, 3 bright stars. So I use this the same way you would use a map. If I'm looking for a faint, distant galaxy, they're quite hard to find. So I use it the same way you would, drive around and use a map. I find a bright star, and then I hop from star to star until I find the faint galaxy I'm looking for. But to do that, you need a high quality map. Modern software, if you have Sky Safari on your tablet, you probably don't need an old-fashioned map. I love the old maps, but the newer software is pretty amazing and convenient as well. So this is my Skirian, this is my high quality atlas. This is the star wheel that I use because I'm old and have bad eyes. So I have a great big star wheel that helps me find things in the night sky, and it spins around exactly the way the others do. I do want to recommend, if you're interested in astronomy, there are a hobby magazine called Sky and Telescope. Comes out every month. Lots of great articles about what's coming up. There's sky maps for the night sky that month in the center. And there's lots of advertisements and articles about telescopes and how to use them and all that kind of stuff. This particular issue is from late last year. And the cover article was on the first picture of a black hole that they took with X-ray telescopes all around the world. And it was a really amazing thing, really cool article. But I very much use in the center is that month's observing guide and calendar. So if there's going to be an eclipse, an occultation, a meteor shower, planets, anything that's happening that month, tells you exactly where to go and how to look at it. Really convenient. Okay. I think we'll call the demo for that so that we can get. How are we doing on time, Carolyn? 8 o'clock. We're pretty good. Okay. And is it's starting to get dark outside? Okay. All right. I'm back. And what we're going to do here is we're going to try and push through the requirements for 4 and 5 and talk a little bit about your drawings and stuff. And then we're going to take our break. So we'll probably go about another 45 minutes to push through the long 4 requirement and 5 requirement. That takes you guys a little bit more work to do those, so I want to be supportive. Some of those you have to do on your own. After we complete 4 and 5, we're going to take our observing break, and you can go use the restroom. But during that 15-minute break, I want you to go outside to your front yard or backyard where you can safely see the night sky. You can use your star wheel. Sorry, someone's talking at my house. See if you can spot Jupiter and Saturn over there by Sagittarius. There are some bright stars in the sky. Directly overhead is Vega, Aquila, Lyra, Deneb, some bright Mag-1 stars that we're going to talk about here in a second. So you can use your star map, and if you think you see Vega or you think you see Deneb or points for Antares and Scorpius, that's a really, really cool one, and you should be proud if you can spot it in the city lights. So we'll move on now to the presentation. All right, constellations and stars. This is number 4, and I'll start in just a second. So the night sky, we already covered. Why do the stars slowly circle overhead? Because the Earth is spinning, and the pole star is the point at the sky that everything rotates around. Constellation just means gathering of stars. And, you know, they take a group of stars in the sky and go, oh, that looks like a turtle, or oh, that looks like a bear, or that looks like a scorpion. Maybe it does, maybe it doesn't. But the point is we give it a name, and that's what its appearance is to observers, and that's why we call them constellations. There's a beautiful picture of a barred spiral galaxy with literally billions of stars. Every one of those stars is a sun. That is roughly what the shape of the Milky Way galaxy is. That's very much our galaxy. If you were able to fly for millions of years out and look back, that is what you would see. We're about 2/3 of the way out in the spiral arm on the right. There is a barred spiral center where the black hole is eating dust and gas and lighting up the crowded center. If you look at it edge on from far away, there's a big bulge in the center. So it's a flat pancake with a bulge in the center, right? And that's where the supermassive black hole is. So the Milky Way galaxy is 100,000 light years across, has over 100 billion stars, and there's billions and billions of galaxies. So it's just mind-bogglingly huge, and the numbers almost you can't imagine. All right. So 4A, identify in the sky at least 10 constellations. So I've combined this information into one slide. So for these 10 things, I've just listed ones that are visible in mostly in the summer sky. So the first one is Ursa Minor Polaris. What that means is the constellation is Ursa Minor, and then in parentheses is the name of the famous star in that constellation. So the constellation is Ursa Minor. The magnitude 1 star is Polaris. So I should probably break those out to make it clearer. And you can use your planisphere or your sky chart to update that. So again, the next constellation is Ursa Major, and the bright star in Ursa Major is Mizar. The constellation Boots has the star Arcturus. Lyra, which is visible tonight up overhead. Lyra is a small constellation, and the bright magnitude 1 star is Vega. Cygnus is right in the Milky Way up above Sagittarius, and the bright star in Cygnus is Deneb. Aquila is the eagle, and there's a magnitude 1 star that's part of the summer triangle on a lot of maps. The star is called Altair. Gemini is in the ecliptic, and the 2 stars of Gemini are Castor and Pollux. So it says 4A, at least 4 of which are in the zodiac. So Gemini, Leo, Virgo, and Scorpio are all in the zodiac, which means the planets and the sun go through them. So Gemini, Castor and Pollux are the stars. Leo, Regulus is the star. Virgo, Spica is the star. And then again, these constellations have lots of stars, but I'm listing the bright magnitude 1s for requirement 4B. Tonight, you're going to look for Scorpio on the southern horizon. And the beating heart of Scorpio is the red giant Antares. Maybe you'll get a chance to see that tonight. So I'll leave the slide up and talk a little bit because you may want to jot some of this down. I can mail out the slides if you need to, or you can go back and connect with the YouTube, right? Okay, so I listed 10 here. The workbook has how many? 8, at least 4 of which are in the zodiac. I should have put an asterisk. So in this case, the zodiac is Gemini, Leo, Virgo, and Scorpio, the last 4 on the list there. Again, all that means is these are constellations in the night sky, through which the planets, the sun, and the moon travel in there as things move around. Remember, we said that planets are wanderers and they move around. So if you've ever heard of, as opposed to astronomy, there's a non-scientific discipline called astrology that seems to try to explain events here on Earth depending on what planet is in what constellation. But that is not science. Okay, so I've left the slide up here for a minute. If you want me to come back to it at the end or have a question about it, let me know. Good luck when you go out tonight. I hope you had a chance to print your sky map, and I at least want you to try and get Jupiter if you can. If there's a really bright street light in front of your house, it's not your fault. You're still going to earn the badge, but give it a try and see if you can see any stars on our break. So we're going to move on now. We've done 4A, 4B. All those stars I listed are magnitude 1 or better. I think it's also in your merit badge book, but you can always Wikipedia the name of the star and look up its magnitude. But they're all going to be really bright stars that you can see in the city with a low magnitude. A magnitude 0 or 1 are the brightest stars. And then as the number gets higher, the stars get fainter and fainter. So a magnitude 15 star, you can't even see with your naked eye, right? So let's see, we're going on to 4C is going to be your Big Dipper sketches. So you go out, you make a sketch of where the Big Dipper is, you come back like an hour later, and you see that it's moved. So I'm looking in that 2 diagrams with the Big Dipper moving around in a circle. So if you come back an hour later, it's not going to have moved very much. That's fine. If you come back 2 hours later, it's going to have moved a bit more. But I want you to understand in making this sketch how the night sky rotates, right? You know, we talk about the moon rising or the sun rising. Yeah, the moon isn't rising, the sun isn't rising. The Earth is rotating towards them, and that's what makes them appear to rise. It's that same point, right? So 4D, explain what we see when we look at the Milky Way. So I've already sort of explained this to you. We're looking at a thin pancake with millions and millions and millions of stars. When we look out along the edge, what we see is just that milky white, and whenever you put a telescope up there, you just see thousands and thousands of stars. They're really far away, so they're so tiny that you can't, without a telescope, tell that they're individual stars. So it looks like a pathway of milk through the sky. That's why it's called the Milky Way. So when you look at the Milky Way, you're looking at a pancake of stars from the inside. And when you look out along the edge, that's when you see all the stars. When you look at a right angle off the pancake, you don't see very many stars because it's a really thin pancake. Okay, 5A, list the names of the 5 most visible planets. So this is going to be those planets that you can see with your naked eye easily. And you're going to list Venus, Mars, Jupiter, Saturn, and Mercury. And that's the wrong order. You might want to list them in order from the sun out to make it clearer to you. So if you do it in order, Mercury, Venus, Mars, Jupiter, Saturn. So that's 5A. Which ones have phases? Well, if a planet is in towards the sun relative to us, sometimes we'll see it to the right of the sun. Sometimes we'll see it to the left of the sun. Sometimes we'll see it with the sun more towards the back or more towards the front. And what that means is Mercury and Venus, which are planets in towards the sun from us, when you look at them through telescopes, they have phases just like the moon. And nobody knew this until the telescope was invented by Galileo, and he looked at Venus and saw phases. And there was a big revelation there. I guess that's 400 and something years ago. But it was like, well, wait a minute. Venus is a globe just like the Earth. And that was really one of the big revelations in understanding our solar system, that it wasn't just a bunch of dots moving around the sky, that the planets are globes like the Earth that orbit the sun. So phases, Mercury and Venus have phases. The next three planets, Mars, Jupiter, and Saturn, Mars is an inner planet, but it's further out from the sun than the Earth. So it is an inner planet, but it does not have phases because we only see Mars as a disk because it's further out. It's always lit up almost completely. Jupiter and Saturn are outer planets, which means they're out past the asteroid belt. Now that diagram that I showed you is way scale wrong, right? Mercury, Venus, Earth, and Mars are all relatively close to the sun. Jupiter and Saturn are much further away. I mean, Jupiter is like 60 times further from the sun than the Earth is. So if this diagram were to scale, Jupiter would have to be, off to your right and, through the wall of your house. Jupiter is really far away. Saturn, even further away. And I won't even discuss, you can't even see Uranus and Neptune without a telescope. So those aren't even visible. People didn't even know they existed until they were discovered in the 19th century. I like this diagram because it has some things. You can sort of see the asteroid belt in there. You can see a comet sort of winging in from the Oort cloud, zipping in towards the sun. When that little cold ice ball gets in towards the sun and starts to heat up, it might have a tail, and we would see a comet from the Earth. But again, the solar system is a disk-like structure. So when we look at planets and the moon and the sun, they all occur in the ecliptic. So let's see, 5A, Venus, Mars, Jupiter, Saturn, and Mercury, phases for Mercury and Venus because they're closer to the sun. And Y is because they're closer to the sun than we are. So you can see a half Venus or a quarter Venus, whereas the outer planets, the ones further out from us, you never see that. You just see pretty much the whole disk. All right, let's see if we can take a look at 5B. Oh, here's a little bit more to scale. 1 AU is 1 astronomical unit. 1 astronomical unit is the distance from the Earth to the sun. So AUs are a convenient way to sort of measure things. 1 astronomical unit is 194 million miles or 151 million kilometers. And Jupiter is what is that, 8 AU or so?
14. No, 4.
Asteroid belt, yeah, I think you're right. I have it at 481 million miles, so you're about right. Saturn is almost out there at 10 AU, which is really far away. Pluto is a pebble in the sky. You need amazing telescopes to ever see those things out in the Kuiper belt. All right. Yeah. Okay, so this is a good chart for 5B. Different planets are visible at different times of the year. So on that chart, you'll start, not with June, but you can start with August 2020 and run it up till, this chart goes to May 2021. So if you can fill it out that far, that's fine. If you can extend it to June, July, and August of 2021, that's good too. You can get this information on your own. I think there's some stuff in the Merit Badge book, but also you could use like the Sky and Telescope sky chart, and it'll show you what planets are visible in the night sky. If you think about it, when the Earth and Jupiter are on the same side of the sun, Jupiter is visible to us on the night side of our planet, out from us. When Jupiter and the Earth are on opposite sides of the sun, to look at Jupiter, you would have to look during daytime, and you'd be staring right at the sun. So Jupiter is not always visible in the night sky. However, right now, Jupiter is in optimal viewing, and it gets better and better for the next few months. Oh no, I guess eventually it starts to go down. So we're in August of 2020. Jupiter's visible right now, but it's eventually going to go away. So really, you just fill out this chart. You list exactly the way. I'll leave it up for a second so you can get rolling on it. You're going to put the months in the year there in the first column. You're going to put Mercury, Venus, Mars, Jupiter, and Saturn. And if you just want to put a check in the month that they're visible, that's fine with me. The main point of this chart is for you to understand that as the Earth moves around the sun, the other planets move around the sun. Sometimes they're visible in the night sky and sometimes they're not, and they come and go. And you just have to look at charts to go, well, is Mars around? I don't know. Mars is now, right now, rising as we speak. That's going to be very close to the eastern horizon. So you need a clear view of the eastern horizon. And I don't think Mars is really visible till around 10 or 11. So I'm not sure you're going to get a chance to see Mars. But if you stayed up till midnight tonight, you could definitely see Mars because it would rise. So anyway, just fill out this chart, put a check for the month and the year in which a planet is visible. This particular chart I have made by having 8 p.m. as my visibility time. If I were to have made this 12 a.m., this would be a different chart because as the Earth rotates 4 hours later, there's a different section of the sky that's visible. So a chart like this is only good for a certain time of night. And I put up there that Sky and Telescope website, that interactive sky chart. I really recommend that one because it has this really cool feature. You can look at the night sky and push the plus an hour, plus a day, plus a month, plus a year button, and you'll see how the night sky changes. And you can then go minus back and forward, and you can see when these planets are visible during these different times if you wanted to do that. Okay. So that's number 5. So 5C, describe the motion of the planets across the sky. Well, first of all, the planets rotate around the night sky with the Earth's rotation. But in addition to that motion, the planets also have prograde motion. That is, they drift across the constellations in the direction that they rotate around the sun. But every now and then, when the Earth passes on the inside track of a planet, or passes on the outside track of an inner planet, what happens is our relative view changes and the planet will actually look like it's moving backwards for a little bit. Now, actually, the planet isn't moving backwards. What's happening is our angle on that planet is changing. So, like, think if you were a NASCAR and you were passing someone low and the crowd passes by, it looks like the guy you're passing moves backwards, but it's not really moving backwards. You're just passing him on the inside track. So, but to us, when we pass a planet on the inside track, it looks for a little bit like that planet moves backwards. And then when we get back around to the other side, it goes back to prograde. And that prograde and retrograde motion, it makes the planet look like it goes forward, and then back, then forward again. It's a really strange motion. This is why the ancient Greek astronomers called them wanderers. They couldn't explain these epicycles with their Earth-centered model of the solar system. It wasn't until Copernicus and a couple other early astronomers figured out that the sun is at the center of the solar system, and that strange retrograde, prograde, epicycle motion of the planets back and forth sometimes is explained by the relative motion of the Earth with the planets. So describe the motion of the planets in the sky, prograde and retrograde in the ecliptic or across the line of the solar system in the sky. D, I'm hoping that tonight we're getting ready to take our break here. I hope that you're going to be able to see Jupiter at least. To the left of Jupiter tonight, about one hand's length, is Saturn. You should be able to see it if you have a clear view of the eastern horizon. If you're not oriented at all, it's important that you orient, right? The mountains of Pasadena should be to your north. The beach should be to your left. The eastern horizon, where things right, would be on your right hand. So turn to face the eastern horizon where things rise. Look for a really bright star that does not twinkle. That's not a star, that's a planet. And that's how you tell the difference. Stars are little tiny, tiny, tiny points of light, and those points of light travel through the atmosphere, which has all kinds of disturbances and waves in it, and they twinkle. But a planet is a disk. Planets don't twinkle. So if you're looking at a bright light, now if that bright light starts to move and come towards you, it's probably an airplane. But I think once you've seen Jupiter, you'll remember it the rest of your life. Look to the left of Jupiter for Saturn, and then you can record 5D. We're going to probably try tonight for Jupiter through our telescope that Spencer, I think, is going to be able to do for us. And so if you can't see a planet with your naked eye tonight during the break, we're still going to cover this requirement, and I hope you'll be able to see Jupiter or one of the other planets tonight. Okay, and I'm still leaving that 5B slide up because that slide has really driven a lot of scouts crazy because they just need to fill it in, and it's the only way to do it. Okay, so 5D is observe a planet, describe what you saw. So 6A and 6B, let's just jump ahead. I'm gonna leave this slide up for a second. We'll probably come back from break and continue talking about this. 6A and 6B are gonna be prerequisite sketches, which you can do from any picture of the moon you find online or in your scout book. Be sure and draw me a picture of the dark areas and the craters, and that should be self-explanatory. You know, we had to fly to the moon and land on it to figure out what those dark areas were. It turns out they're lava flows that settled out, and of course we didn't know exactly what formed all the craters. Someone thought it might have been volcanoes on the moon. But as it turns out, as many people have thought, the craters on the moon are caused by things slamming into the moon. And the moon is covered with craters. If you think about it for a second, why isn't the Earth covered with craters? I can hear the gears turning out there. Is the moon just really unlucky and gets hit by meteors all the time and the Earth doesn't? Well, I told you I was out looking at the Perseids meteor shower a week ago, and I saw a dozen big things zip across the sky and light up. Well, we have an atmosphere that blankets the Earth, and when
the meteors burn
right,
they burn the atmosphere.
Right, they burn up in the atmosphere, right? So there are no craters on there. Very few craters, only really big ones make it through, and even then, we have water and wave and erosion and continental drift that erases them. The moon has no atmosphere, it has no wind, it has no water. So every meteor that has ever hit the moon, from a tiny one the size of a BB all the way up to a big one, has left a hole, and they're all still there. So the moon is just covered with craters. So 6B, you're gonna have to sketch me 4 consecutive nights of the moon. Right now, the moon is rising really early in the morning and is not visible in the night sky. So you can either do requirement 6B by getting up early in the morning, or you could wait 2 weeks till the moon is visible. I don't recommend that because I'd like to see you get your blue card real soon. If you want to use an interactive sky chart to show where the moon's different positions are on 4 nights and what its phase looks like, I will certainly accept that. The point of 6B is that you sketch what the moon looks like and where it is in the sky 4 nights in a row at the same time so that you can gain practical experience in how the moon changes from night to night, what the different phases mean, and why it's changing that position. So there's some stuff in your scout book that'll help you figure out 6A and 6B, lots of stuff online and all that. Okay, how are we doing on time, Carolyn? $30. Okay. I'm gonna go about 10 more minutes, then we're gonna take our break, and then we'll reconvene for our observing and our career stuff and all that. So 6C, really, really easy one. What factors keep the moon in orbit around the Earth? There are 2 forces that exactly balance each other to keep the moon going around and around the Earth. One of them is gravity. Gravity, large masses bend space in such a way that mass attracts mass. So the Earth, which is gigantic, and the moon, which is pretty big, are attracted to each other. So without some other balancing force, the moon would just drift in and crash into the Earth. Gravity pulls the moon towards the Earth, and the moon, to a lesser extent, pulls the Earth towards itself. They're mutually gravitationally attracted to each other. So why doesn't gravity just pull the moon down? Well, when the moon was formed, it was spinning. And so there's an inertial force, which is the same force as driving a car really fast in a straight line. The moon is moving, and it's moving really, really fast. And that motion, if you were to just turn gravity off, the moon would fly away from the Earth at a really high rate of speed. So if you've ever been on a ride at an amusement park or on a playground that goes around and around, you can actually feel the force pushing you away as things spin around, right? So say you're sitting in a ride that's spinning you around. If it weren't for the chair you were sitting in holding you back, you would just fly off out into space. So these two forces, gravity pulling them towards each other, and the motion or inertia of motion pulling the moon away, they're perfectly balanced to hold it right where it was, and it just keeps going around and around and around. If you were to put a rocket on the moon and push to speed it up, it would move further away from the Earth. If you were to put a rocket on the other side of the moon and slow it down, it would gravitate down towards the Earth. So speed and motion are one factor, and gravity is the other, and they're perfectly balanced. In 6D, there is a chart of the relative positions of the moon. What I want you to do in 6D is for each of those boxes, using your scout book, the chart you see in front of you, and your understanding of geometry, just write down in that box whether it's a new moon, a full moon, a half moon, or a crescent moon. And you do that by thinking, okay, there's the sun, and that E is the Earth, and that M is the moon. Think of the rays of the sun traveling towards the Earth. What part of the moon is it going to illuminate? And is that going to appear as a new moon, a full moon on the opposite side, a quarter moon, which is half illuminated, or a gibbous moon, which is 3/4 illuminated? So in your scout book, I'm going to give you an initial hint. The upper left box shows the light of the sun traveling towards the moon, lighting up the side of the moon facing away from the Earth. So if you were standing on the Earth looking at the moon in that diagram, you wouldn't see any of the lit up side. New moon is when it's completely dark. The full moon, which in your workbook is the upper right box, is the exact opposite. The moon is out from on the other side of the Earth. The rays of the sun illuminate the moon, and you see the complete disk. So on 6D, just write down what the different phases are for the different position of the relative position of the moon and the Earth. And you can always see the diagram in front of you will help you figure that out. The diagram in your merit badge book does the same thing. But the point of this exercise is to understand why it's a new moon. And then as the moon comes around as a waxing crescent, and it gets brighter, and then it's a quarter moon, you can actually understand in your mind that that's the moon orbiting the Earth, and you're just seeing a different view of the moon as it circles around the Earth. Okay, so I think we made 1 through 6 with good time tonight. I hope you guys got good notes for your packet. I hope I've provided resources and methods for you to complete your packet. I certainly look forward to receiving that. We're going to finish up 7, 8, and 9 after our break. So at this point, I'm going to call what time is it? 8:40? 8:30 something. Okay. What time? Like 8:50? Would that be a 15-minute break? Okay, so 15-minute break. During this break, you can get up, stretch around, use the restroom. But during this break, I'm asking you to go outside to whichever yard is safe and dark, and just see what you can see. Use your sky chart. If you just find one thing, when you come back in, whatever you see, I want you to type in the chat so we can all see who was able to spot stuff. So thanks a lot for listening to the long lecture to fill out that workbook and all my stories. I hope you have fun observing tonight. When you come back, we're going to go to some live viewing sessions. So I'll see you in 15 minutes.